Let's look at precipitation reactions and look at the stoichiometry of it. So if you could get into the beaker and look really closely, you would see that you have the ions in solution. So there's your barium nitrate, and there's your potassium chromate. When they go together, they form the precipitate barium chromate, which has this yellow color. The potassium and the nitrate are still in solution in here. So that has your, try to write this again, the nitrate ions in solution and your potassium ions in solution. So another representation, you can see your potassium ions and barium ions. So there's your potassium and your barium ions. Those are your cations. And then you have your nitrate and your chromate. When the barium and the chromate get in the same container, their solubility decreases and precipitate out of solution. So if you look at potassium chloride in silver nitrate, it forms a white precipitate, which is silver chloride. So looking at this, here's your potassium chloride in solution, your silver nitrate. Again, when they get mixed together, your silver nitrate combines with your potassium chloride, and the silver chloride precipitates out of solution. So when we describe these solutions, we have a formula equation, a complete ionic equation, a net ionic equation, and we're going to look at sodium hydroxide and iron 3 chloride. So sodium hydroxide, NaOH, in solution with iron 3 chloride, FeCl3 aqueous. When you mix those two solutions, you get NaCl plus FeOH3. NaCl always dissolves in water, and this does form a precipitate, which is this iron 3 hydroxide. To balance, we need a 3 in front of our sodium chloride and a 3 in front of our sodium hydroxide. So the formula equation is just your regular balanced equation. Your complete ionic equation, you take your formula equation and you pull it all apart so you can look at the ions. Whatever is a solid, you keep together. So sodium, we have 3 ions of sodium, and it's AQ plus 3 hydroxide ions, AQ plus the iron, Fe with the 3 plus charge, and it's with chloride, and we have 3 chloride ions, AQ. On the product side, we have 3 sodium ions and 3 chloride ions, because the sodium chloride is in solution. And you write it below, our solid is FeOH3, and you keep that together. So there's your complete ionic. Your net ionic is to take the solid as your product and combine the 2 ions that make your product. So your net ionic, and I like to write the cation first, is iron 3 plus your 3 hydroxides, so you still need to balance, forms your FeOH3 solid. The sodium and the chloride in this reaction are called spectator ions. We have some rules for solubility, which we'll work on. This is just one way of looking at it. If you play your Mahjong 10 app, that will really help you memorize your solubility. If you have a nitrate, it's almost always soluble. If you have a group 1 salt or an ammonium ion, it's soluble, so it's the aqueous one. Your halogen salts are usually soluble, but not if they're silver, lead, or mercury 1. Sulfate salts are usually soluble, but again, not barium, lead, mercury 2, or calcium. most hydroxide salts are only slightly soluble. Yeah. And most sulfides, carbonates, chromates, and phosphates are only slightly soluble. So if we look at potassium nitrate and barium chloride, when they combine, they would make barium nitrate, BaNO3, plus KCl. And we're supposed to figure out, do we have any solids? Well, a nitrate's soluble, and a chloride or potassium is soluble, so there's no solid here, or no reaction. When you look at sodium sulfate and lead-2 nitrate, let's put it down here. Our products are sodium nitrate, NaNO3, plus lead-2 sulfate. Lead sulfate would be your solid if you check your solubility rules. Our next one is potassium hydroxide with iron 3 nitrate. We get potassium nitrate as a product plus iron 3 hydroxide, and we just worked with this. The iron 3 hydroxide is your solid. I encourage you to always check before you really believe you have these things memorized, but do work on memorizing your solubilities. So let's look at stoichiometry a little bit. So we have a mixture of silver nitrate and sodium chloride, and we want to figure out how much sodium chloride do we need to precipitate out all the silver ions. So on this, my first step is to put in a new slide. I think I'm going to run out of room. So do that. Okay. Let me just do the next one. I think I'm going to need it. All right, let's go here again. So first thing I would do is write a balanced equation. We have NaCl. Oops. Let's try it again. Oh, it's not going to write. Let's see if I can get it to work. Do that. Maybe that'll work. So we have NaCl plus silver nitrate, AgNO3. It reacts to give you AgCl, that's your solid, plus sodium chloride. Notice that it, oops, sodium nitrate. I'm a little frustrated because my things aren't working. That's okay, we'll make it work. NaNO3. Everything else, this will be aqueous, this will be aqueous. This starts out as a solid and then dissolves. We have 1.50 liters of silver nitrate. It's a 0.100 molar solution. So if we just use M times V, we'll find out the number of moles. Notice it's a 1-to-1 relationship. So we get a lot of stuff right there. If I take my volume, I'm going to use M times V equals N for my silver nitrate. And I have a 0.1 molar solution, and it's a 1.5 liters amount, so I have 0.15 moles of AgNO3. It asks, how many grams of silver nitrate do I need? Or, excuse me, silver chloride. So, because it's a 1-to-1 relationship, I have 0.15 moles of AgNO3. If you look at your balanced equation, you need the same number of moles of sodium chloride. So I know I need 0.15 moles of NaCl. Those guys go away. So all we need to do now is change our NaCl from moles to grams. 0.15 moles of NaCl times, sorry, what that is, 1 mole of NaCl has a molar mass of 58.44 grams. multiply that through, I believe I'd have 8.77 grams of NaCl needed to react with all of that sulfur nitrate. So what about, now there's a typo here. When aqueous solutions of sodium sulfate and lead nitrate are mixed, sodium sulfate precipitates. Calculate the mass, I think I said that wrong, of lead sulfate formed from 1.25 liters of a 0.05 molar. This should be lead nitrate there. And so let me change that. So this is PbNO3 2. So we want to know the mass of one of the products. So first, the balanced equation. Sodium sulfate is a solution. It's combined with lead 2 nitrate. It creates the precipitate lead 2 sulfate, and sodium nitrate is in solution. It's a limiting excess problem, so we have 2 liters of a 0.025 molar solution, and here we have 1.25 liters of a 0.05 molar solution. So using M times V for each, I'm going to figure out how many moles I have, and let me just change colors so you can follow it perhaps a little bit more easily. So using M times V equals N, I know I have for sodium sulfate 0.05 moles. For the lead 2 nitrate, I have 0.0625 moles. So since it's 1-to-1 for reactants, I know that this guy is the limited. You're going to take the smallest one, it's 1-to-1. So now, using the limiting, I can go from sodium sulfate, oops, not there, huh? We're going to, there we go. Let's get a color, there we go, I don't believe. We're going from our sodium sulfate to our mass in grams of lead 2 sulfate. So, let's start with a 0.05 moles of Na2SO4, which was our limiting. It's a 1-to-1 relationship. For every 1 mole of Na2SO4, we create 1 mole of lead 2 sulfate. Lead 2 sulfates has a large molar mass. I've calculated 303.27 grams. Please do check my work late at night, getting things done. So the units cancel, and we multiply things out, we get 15.2 grams of lead 2 sulfate, which would be the product of that reaction. When you have an acid-base reaction, your net ionic is your hydrogen with your hydroxide produces water. And we can use that shortcut of M1, but let's change it to A for acid, E for volume of acid, molarity of base, and volume of base, because I know that these combine in a 1-to-1 ratio. So I know if I have HCl and I combine it with NaOH, I'm going to get H2O and NaCl, and it's all 1-to-1. So we're going to figure out how much acid we need to neutralize our 25 mils of 0.3 molar. So, let me write this properly. So we're going to take our volume of acid, and there we go. All right, so we have 0.100 molar HCl. I'm going to put VA, keep myself straight. I have 0.350 molar base. And I'm going to keep 25 mils because I'm going to find the volume in mils. So VA, when you do your mathematics, is 87.5 mils of your HCl. Our next reactions are oxidation-reduction reactions, and we'll spend quite a bit of time on here, but it's just the trading of electrons. So if you have pure sodium and pure chlorine, sodium will give up an electron to become a sodium ion. Remember, loss of electrons is oxidation, gain of electrons is reduction, and we'll look at those much more thoroughly in the days to come.